So we were seeing the solution of algebraic and transcendental equations. So let's now apply Newton-Raphson method. We have already seen uh, bisection method and method of false position. So let's now see the third method, which is Newton-Raphson method. Okay. So here the idea works like this. Let me just explain first the maths and then the graphical representation I can explain. So let x naught be the root, be the approximated root, approximated or approximation root or approximate. I mean, it's basically not the exact root, the approximated root. Now, if x1 is x naught plus h, let x1 not be the exact root, be the exact root of f of x. Then you can say that f of x1 is also 0. So what we are assuming is x naught is some approximated root, x naught plus h is exact root. Okay. Now we use Taylor series to expand. Okay, so we can expand f of x naught plus h. So expanding this f of x naught plus h, we can write f of x naught plus h into f dash x naught plus h square by 2 factorial f double dash x naught plus so on. And this is 0, right? Because x naught plus h is the exact root. Now, since h is small, now if suppose it happens that you are able to find out h from this entire equation, then you can directly get the exact equation. It's not some approximated root or nearby root which you can near to the root. You can imagine some point, and then you can calculate h from this equation, and the job is done. Okay, you can just add h which you have calculated from this x naught plus h will be the exact root. But that's not the case because it's very difficult to calculate h from this root because it has a lot of powers, okay, and a lot and infinite terms. So what we do is we make an approximation that h is small, so we neglect h square and higher powers of h. So in that sense it will be f of x naught plus h f dash not, the higher terms are not there, is equal to 0. So h will be minus f x naught by f dash x naught. Okay, so this is the approximation. So a closer approximation, when you cannot say that this h is exact, so obviously x naught plus h will not be exact, but it will be a closer approximation. So closer approximation is x naught is equal to x naught plus h, which is x naught minus f x naught by f dash x naught. Okay, so this is the closer approximation. Now similarly we'll be starting with x1. You can get a still better approximation h2. So h2 will be your x1 minus f x1 by f dash x1. Okay, this is your h2. So in general, let's write down in, because you can repeat the process uh, many times in order to get the desired accuracy. So in general you can write xn plus 1 is equal to n xn by f of xn by f dash xn. So what it means is, if you know xn, you can calculate xn plus 1, which is a closer or a better approximation of the root. Okay, now let's see how this can be understood in a very easy way from the graphical representation. So how do I explain graphically? Well, a graphical representation is something like this. You have the root, okay, something like this. So let's say that this is it's not, and this point at which uh, the abscissa is it's not, the ordinate is f of it's not. Okay. Now the idea here is draw tangent. Okay, draw tangent. Uh, there's some problem with this drawing board. It doesn't. That's quite sensitive. Let me try it again. So if I say that this is the curve and this is the point, okay, and this point is it's not f it's not, sorry, this point is it's not, and this point a is it's not f of it's not. Now this is basically a tangent. Okay, this is a tangent at a, tangent at a, right? And the point at which it intersects, okay, that point, let's say it's one. Okay, and now similarly what we are doing is it is now we are reading a different point a1 on the curve. Similarly, now we draw a tangent, okay, which again meets, we meet somewhere here, which is h2, and similarly you proceed it, and this is a2. So that is the thing. So what we do is, so this can be understood in this way. Basically, starting from a point, drawing a tangent to the curve, then the point where the tangent meets the x-axis, that is your new abscissa, and the corresponding point, you'll again draw a tangent, and this process you will repeat until you just become very close to the root in the desired accuracy. Okay, so the same thing we can derive it graphically also. So the equation of tangent at a, which is it's not f of it's not, is basically y minus the value y minus y naught is equal to slope, which is the derivative, to x minus x naught, x minus x naught. So that is your, that is your the equations. Now we need to find out where it cuts its axis, right? Because then we can get the new better approximation. Okay, so it cuts its axis when y is 0. So putting y is 0 in the top equation, we will get x1 as x naught minus f of x naught by f dash x naught. Okay, and this is basically your first approximation to the root. Okay, now then a1 is the point on the curve corresponding to x1, and now draw the tangent. Same thing, now you will just repeat the process. Draw the tangent at a1, which will cut the x-axis of x, cut the x-axis at x2. Okay, so this is closer to the real root, somewhat closer. Okay, so and the second approximation, the root. Okay, So the process is repeated until desired accuracy is obtained. Accuracy which you feel okay, this is the required accuracy is obtained. Okay. So this is a simple method. A sometimes is based on tangent. This is called a tangent method sometimes, and we have the general formula also we have seen. So the general formula is hn plus 1 is hn minus f of hn by f dash hn. So we'll try to put everything in this general form and then solve the problems. Okay, so let's now solve some problems based on Newton-Raphson method. Find the root near to x is equal to 1. It is 3x is equal to cos x plus 1. Knowing that, the root is lies somewhere near 1. Okay, that's what it has given. So this is your f of x. So f of x is basically 3x. So you have to always put in this form f of x is equal to 0. So that's the idea. Okay, that's the idea. And f dash x is basically differentiation with respect to x. This is 3 into dx by dx minus d by dx of cos x minus d by dx of 1. So this is 1, cos x is sin x minus sin x. So this is the thing, 3 plus sin x. Okay, so in general I can write hn plus 1 is equal to hn minus f of hn by f of hn plus 1. So this can be written as hn minus f of hn is 3. We substitute hn in the place of x by f of hn plus 1. F dash, oh, sorry guys, this is f dash hn. So f of hn by f dash hn, and f dash hn will be substituting hn there, so 3 plus sin hn. Okay, that's the thing. So now if you just resolve this, it will be hn 3hn plus 3 sin hn minus 3hn plus cos hn plus 1 by 3 plus sin hn. Okay, so now 3hn will get cancelled. You will get, and there is hn here, don't worry, there is hn here. So it will be, and there is no 3, slight mistake, 3hn and hn sin hn. So you will get, finally after simplification you will get hn sin hn plus cos hn plus 1 by 3 plus sin hn. So this is what you will get. Okay, a general formula relating hn plus 1 and hn. So now you can just start with hn is equal to 1. Hn plus 1 will be, you have to just substitute 1 here, 1 sin 1 plus cos 1 plus 1 by 3 plus sin 1. This if you just calculate, you will end up getting 0.6685. You have to use a calculator. Calculator is allowed, so you can just use it. Similarly, now let's calculate. So this was all about h2. Okay, so h2 was 0.6685. Now similarly, I'll calculate h3, which is nothing but h2 minus f of h2 by f dash h2. Same thing, I'll put now consider n is equal to 2 in this expression. So I'll get h3 as 2. It's n is 2. Okay, so this is h2 sin h2 plus cos h2 plus 1 by 3 plus sin h2. So just have to substitute whatever we got, 0.6685 into sin 0.6685 plus we get cos 0.6685 plus 1 by 3 plus sine 0.6685. So this is what you will get. So if you just simplify, you will get 0.666. So similarly, you can, build till the desired accuracy. He has not asked, so you can just stop it at this point as well. But you can just proceed like till like here already we got say till 2, till decimal 2 places we got desired accuracy. So you can continue there. If he has asked 3, you can continue to the 3. So let's solve another problem, basically which we have solved. This problem we have solved in the method of false position. We have solved this problem. Okay, so the equation, this is your f of x, and there it was written that the root lies between 2 and 3. Okay, so we'll take that. So f dash x was 3x square minus 2. Okay, so now substituting the general formula, we'll get xn is basically substituting xn only. F of xn is basically substituting xn in the place of x in this expression, and f dash xn is substituting here 3 xn square minus 2. So this will be basically, if we simplify, it will be 3 xn whole cube minus 2 xn minus xn whole cube plus 2 xn plus 5 by 3 xn whole square minus 2 minus 2. Okay, so if you simplify this further, this will come out to be 2 xn whole cube plus 5 by 3 xn whole square minus 2. So these terms will get cancelled. Okay, that's the idea. Okay, so you brought a directly relating xn plus 1 and xn in one form. You brought that. So now it's just substitution. Okay, so you can just substitute at n0, starting with n0. So n0 means x1 you will get x0 whole cube plus 5 by 3 x0 whole square minus 2. Now what value to it? So we'll take the rightmost value, because this is a tangent method and it basically begins uh, from the, you can start from the left hand also, but then if there's an option, you just better start with 3. So it's not, let's let it be 3. So from this we can calculate, it's 2 into 3 q plus 5 by 3 into 3 square minus 2. So this value comes out to be 2.36. Similarly, when n is equal to 1, you can write x2 as, you have to now take x1 here. So 2x1 whole cube plus 5 by 3x1 whole square minus 2. So 2 into 2.36 whole cube plus 5 by 3 into 2.36 whole square minus 2. So this value comes out to be 2.12. So remember this, we have to solve correct to 3 decimal places. Okay, the question is same as which we solved in the method of false position. Okay, so we have to get to the level of 3 is equal to. Similarly, n is equal to 2, you will have x3 as 2 into 2.1271 whole cube plus 5 by 3 into 2.1271 whole square minus 2. So this value, if we compute with the help of a calculator, we are writing till 4 decimal places. So that is 2.0951. So similarly, for n is equal to 3, it will be x4 is equal to, what is that, substitute this, it will be 3 into 2.1, n is equal to 3 you're solving, so 2.905 whole square 51 whole square minus 2. So this value comes out to be 2.0954. Okay, and n is equal to 4 when I substitute, so 2 into 2.0953 plus 5 by 3 into 2.0945 whole square minus 2. So this also comes out to be 2. So I'm writing till only 4 digit. Okay, so we can see that till the third value is same. In fact, the four, it is now accurate to a 4 digit. So but we are sure that it is 2.0994. This, that is one thing which we can guarantee. Okay, so the approximated solution by this Newton-Raphson method is 2.094. It's the solution of this expression. So we have basically seen three methods here. The bisection method, which works on bisecting the interval into half every time and then checking for the roots in the interval, and that's the idea in which it approaches to the real root. Then we saw the method of false position, where the idea was to join 2 points on the either side of the root. Okay, and then look at the x-intercept of the line joining, or the chord between the end intervals, the chord joining between the end points where it meets the x-axis. So that is your x-interval, and then that is your so that is another. From there, then you have to check on either side where in which interval it lies, and so on. You have to proceed. Newton-Raphson, it's basically a tangent method, starting with the approximated root. Draw a tangent, see where it meets the x-axis, and that becomes the new abscissa. So corresponding to that, you have a point on the curve. Then again draw a tangent from this new point, and so on, just proceeding towards the real root. So you will be getting close to the real root, and once the desired level of accuracy is reached, you can stop the iteration at that point of time.